All right, so we're going to talk about integrating vector valued functions. So because of the way that we defined differentiation of vector valued functions, we can say that for R of t is f of t I hat plus g of t j hat plus h of t k hat. And we're saying that our f, g, and h are continuous on our interval. They're nice functions. The integral, indefinite integral, r of t dt, is we just integrate each component. The integral of f of t dt I hat plus the integral of g of t dt j hat, we just integrate component by component, just like we'd expect. And a definite integral, if we're integrating this on some interval where our functions are behave nicely on that integral, we just do the definite integral of each component function. So basically we do, for these kinds of problems, we get to do 3 problems in one. Yes? Yes, and we're going to talk about that here in just a second. It depends. What it represents depends on what R of t represents. So basically, you're just adding up a bunch of function values.
So there's no geometric relationship unlike in previous times.
Right.
Like we had the drawing.
Right, right.
There's none of that. It's just
All right, and I need one other thing here. Plus c. On my definite, I need a plus c here. The constant of integration is a vector. Oh, here we won't have a constant. So we do get, we end up with three constants of integration, but it's, so we get one vector. So this would give our x component, our y component, our z component. We combine them into one vector. And for a definite integral, we would need, we would have initial and final conditions. That's what's going to determine our constant of integration. So be careful. So we can write the integral of r of t dt equals capital R of t plus c, where capital R prime equals r. We have to be careful because our constant of integration is a vector constant. All right, So just like we'd expect, we integrate component by component, just like we differentiate component by component, just like we take limits component by component, just like we test for continuity component by component. All right, questions there? Okay. I have a few questions for everyone. All right, we have a particle. And it's moving on a sphere. Centered at the origin. And I guess these are all true or false. So we have a particle moving on a sphere centered at the origin. So some it's in a gravitational field and an electric, something like that. The derivative vector, and this is the derivative of the position.
Is there a velocity vector?
So the derivative of the position vector is tangent to the sphere. So this is asking for any value of t, the derivative vector of the position vector is tangent to the sphere. True or false?
It should be, yeah. The particle in a sphere is velocity.
True. What would happen if the velocity vector were not tangent to the sphere?
It would not be on the sphere anymore.
There would be some component of the motion, some component of the velocity, either away from the center of the sphere or towards the center of the sphere, and it wouldn't stay on that sphere. So if it's moving on the sphere, then the velocity vector has to be tangent. So that's going to be true. The definite integral of a vector valued function is a real number. Yeah, it's false. It's a vector. And here I'm going to say otherwise true, otherwise particle moves off the sphere. All right, this next one is a little trickier. The derivative with respect to time of the magnitude of R of t is the magnitude of the derivative of R of t.
No, that would be different. You have to, the first right, you don't. The first one you get a number up first. It's like,
First one you get 0, second one you get a number. False.
No, you don't get 0 at first.
Oh, I guess
It's not a number.
Not a number.
It's
Yeah.
the first one you take the magnitude first. That would just be 1. Because that's, the magnitude of R is just a number.
So it is here, let me do this. R of t
not LA.
Could the magnitude vary in time?
Yeah.
Yeah. Because it's a different it could be moving different distance from the origin, right? So this is not necessarily 0. And what does this represent?
You do the derivative and then the magnitude. The magnitude
So
of the
this, if we're thinking of a particle moving, what is this?
That's the velocity
Magnitude of the velocity, which is, what do we call that? Speed. So that's the speed. And what is this? That's just a derivative of the magnitude of the position. So are these the same?
No.
Can we think of an example? I think you were thinking along the lines of my counterexample, Jack.
Well, you can create an example where one of them is 0 and the other one is not.
What kind of motion would be, one of them would be 0 and the other's not? When the magnitude of the position vector doesn't change in time, but the speed might change in time, but the speed, so what kind of motion would the magnitude of the position vector be, the derivative of the magnitude of the position vector be 0? A circle. How about something moving in a circle? The magnitude of the position vector is what? The radius of the circle, right? The magnitude of the position vector is the radius of the circle. And the derivative of that is 0. So for circular motion, and I think this is kind of what you were thinking of, Jack. For circular motion, the d dt of the magnitude of r of t equals 0, because r of t equals the radius of the circle.
So this could be true, but it doesn't have to be.
It could be true, but it doesn't have to be. And the speed of a particle moving in a circle, the speed is constant.
It's in the
So this one's a little trickier. So for uniform circular motion, so something orbiting in a circle, the speed is constant. So this is false. Because all we need is one counterexample to say something is false. For uniform circular motion, the speed is constant. Is the velocity constant? No, because what's happening to the velocity? It's changing direction. And we're talking about a vector quantity, so the velocity would not be constant. It has constant magnitude, but it's changing direction. All right. Last one. The derivative with respect to time of r of t dot u of t is r prime dot u prime.
No.
No, that's not true. We did this.
No?
Theorem 12.2.
What do we have to do here?
R prime dot u prime plus R.
Dot
We-
product.
No, R prime.
Yeah, yeah.
We have to use a product rule.
What I meant to say.
Either the product rule, or we do the dot product first and then take the derivative, which is probably easier. It depends. Depends on the. All right, questions? Okay. That's it for today.
take a whole bunch of interviews. How fun.
Wait, what?
So in this case, we just do the same thing we did over and over again. Are all of the units just this?
No.
Oh, good.
Now go on.
So you guys are on the same page.
So what we're doing here is we're building up, we're putting